I'm going to give you a brief overview of some of the work I've done in my PhD, specifically looking at ways to sort of improve the magnetic telluric response function using different geophysical methods. So again, just a brief overview that Oleg just gave, but I'm obviously Wesley Harrison. I completed my PhD last year, October, so still pretty fresh with everything. But I mainly specialize in electrical and electromagnetic methods, and specifically magnetotellurics is obviously my favorite. Just a quick sort of introduction to MT for some of the guys that just need a bit of a refresher. So MT stands for magnetotellurics, and magnetotellurics is obviously a passive source electromagnetic method used to understand the conductivity structure of our subsurface. MT measures both the electrical and magnetic fields for different frequencies and times, and from there we can calculate the conductivity structure. Just a brief overview of the passive sources for MT. Spherics is the high frequency sources, above 1 Hertz really, and it's mainly due to lightning strikes near the equator within the waveguide. And then the low frequency sources generally come from micropulsations. This is just the interaction of the solar winds with the magnetic field producing magnetospheric induction, creating a very low frequency source for MT. And this is important because MT is one of the, I suppose, the two geophysics methods that can really survey pretty deep, the other being seismic. So this is what makes MT a really good geophysics method to consider. So the start of my PhD journey actually starts in a small town in the northern parts of the Western Cape called a town of Hopefield. I was invited basically to go down with a local contractor to go survey some farms to look for groundwater. This was during the 2018 drought that we had, and they were really suffering. Now, the problem with the Hopefield area is that there's just the sand in the area. There's no real outcrops of rocks. And this means that you really do need geophysics. So we managed to then conduct at least around 8 or 9 AMT surveys, AMT being audio magnetotellurics. So it's our higher frequency MT for the near surface. And we actually had a look to see if we could primarily map a conductive feature in the area that is the calcrete layer. And the problem with the calcrete is that the drilling rigs struggle to actually drill through this layer. So our primary objective was to map this and try and figure out if there's any breaks in the calcrete. So we did this, and you can see on the top left image here, we have some resistivity inversion images that we managed to see some breaks in the calcrete, and we then sank a borehole there to actually then reach the aquifer lying beneath. And this little blue line here represents this this driller here. We were able to map the calcrete within a 2 or 3 meter accuracy, which was pretty good. But one of the main problems and one of the main reasons for the PhD work I've done is that, as you can see underneath the calcrete layer, which is primarily conductive, there's very few structural, signatures in the aquifer that's underneath it. And this is because it's resistive. And one of the problems with the EM method in general is that if you have a conductive feature overlying a resistive feature, it will tend to get masked. And this is just a natural physical behavior of EM, that it's naturally sensitive to conductors. And just to highlight this, I actually took another MT inversion that we did in the same area. The white is just, I did an analysis to see which areas were of least confidence, and I just put white cells. It's just to make sure we don't overinterpret zones of poor confidence. But where we had areas where the conductive overburden was actually broken in stages, you could actually see some structure in the aquifer. And if we had this conductive calcrete continuous on the top here, we would not really see any other structure. So this is really one of the problems. And just to show this in theory, if it still doesn't make sense, let's just take a very simple theoretical model. So we have a 10 ohm meter conductive overburden with a 8,000 ohm meter resistive dike embedded in a 1,000 ohm meter half space. And if you guys remember from all your geophysics modules that you need a physical property contrast for any, to map any type of change in geophysics. So this would make sense because we have a 10 ohm meter, overburden, and just underneath it is an 8,000 ohm meter conductive resistive dike. So let's see what happens when we do the inversion. So when the inversion is done, you can see we do map the conductive overburden, but the resistor is lost. Now this is one of the issues I wanted to tackle, and this can't really be fixed with advanced inversion modeling or signal processing. I'm sure there might be some ways, but this is more a physical problem. It's in the physics itself. So this means that I had to actually go back and go to the basics. So I went back to Maxwell's equations, good old Maxwell, with the governing equations of electromagnetics, to just investigate this whole physical phenomenon further. And by doing this, I had to think of possible other ways that could assist the MT data and inversion. So one of the methods that I came across and one I had readily available was the electrical resistivity tomography method, so ERT. And ERT is generally not as sensitive to conductors as MT. And this made good sense to try and combine the two and just see what we could do with the two methods. So what I ended up doing is rederiving the Maxwell's equations and then also deriving the current density equation for MT, which isn't trivial even for simple shapes. And I did the same for the ERT method. So we ended up with two current density equations. And then we ended up with the two equations for current density. And I found that the sigma is the material conductivity, which is the same between the two methods. So you can actually then combine the two methods and actually connect them. So it ends up giving you a very simple equation that looks a lot like Snell's law, which just enables you to move between MT data and ERT data interchangeably. So you can create this sort of pseudo MT data as you would like. And again, this is just a simplified analytical derivation. There's quite a lot more to this, but it's in review at the moment. But just to show you the more realistic version is here on the right, and this is the condensed version. So now we have an analytical solution to combine the two methods. So that's a good first step, and this was quite a big step initially. But now we have to apply this realistically now. So I then did some brute force just tests to have a look at what we can do with the two data sets. So on the top, we have our just the model, a theoretical model. And then on the left, we just have an MT inverse model with only MT data. On the right, we have an empty model where I calculated the high frequency data from the ERT data, theoretical data. So we ended up augmenting the data. So on the left, again, we see that we don't really see much of the resistor again in the near surface, but we start seeing it, maybe deeper on, but we lose most of it in the near surface. While in the augmented space, where we actually created high frequency pseudo empty data from the ERT data, we start to slowly see the resistor starting to appear again. And this can again be seen just in the sensitivity models. So over here, you get the very characteristic panther-leg structure where there's no sensitivity below really the conductive overburden. But when we look at the model sensitivity of the augmented function, we actually see that the sensitivity is actually constrained to the conductive overburden, and the low sensitivity is by the resistor features. Now, sensitivity in the inversion model just gives you a measure of how much those cells have an effect on the inversion routine. So generally in MT, conductive features, small changes in conductivity, so very conductive cells will have quite a big change in the inversion, while resistor features need quite a big change in resistivity to have an effect. So you ideally want your most sensitive cells to be near conductors and your poorest sensitivity cells to be by resistors. So we do have some sensitivity below the conductive overburden in the augmented function. So basically what the function then looks like is that we actually add high frequency data from the ERT data, and we have this deadband that is in the AMT data that we can actually overcome and include in the high frequency data. And we we then just named this new function the augmented ERT empty response function. It's just a combination of the ERT data and the empty data. So now to show that what this looks like in practice, we just have a simple forward model, 1D forward model of a conductive overburden and a resistive half space. And the red represents the pseudo-empty data from the ERT method, and the blue just represents the standard, empty data that we collect. So this is just to show you what the response function components are and what they look like. So we have the two halves. All right, so we have an analytical derivation that we managed to simplify so we can get the two methods at least speaking to each other. Now we've actually combined them together to create an augmented function of high frequency pseudo-empty with our standard empty. All right, so the next step is to actually test this in inversion algorithms. So what we did is started with the 1D inversion modeling. So the black line here is the true model. So we're trying to get as close as possible to the true model as we can. The red lines just resemble the empty 1D inversions that we did with just the empty data. So if you take the red out of the previous curves, and the blue resembles the inversions we did with the augmented ERT empty response function. And as you can see here, the inversion models making use of the augmented function got closer to the real model than the standard empty. And in some cases, we came up with an improvement of up to 91% in the recovery of the true resistivity model in 1D. This is pretty good, and 1D inversions are still pretty popular, and there are many environments where 1D empty is still very relevant. So this is a good start to our test. So we do see improvement in the 1D space. But then we decided to move it over to the 2D space just to have a look and see how it compares there. So again, our first model is the model we would like to recover. We have a conductor overburden and then our typical resistive dike in a half space. The empty inversion that we used, a typical empty that we would see, again, struggles to see the dike at those frequency ranges, and even sometimes the overburden. But we do see at depth it's starting to get the resistor feature, but we're missing quite a lot of it in the near surface. But then in the augmented ERT empty response function, we actually start to recover quite a lot of the resistive dike below the conductive overburden. And we managed to actually map the overburden itself. Now, the overburden is slightly more conductive. This is just because of the simplified current density that we used in the empty response function. This can be improved, obviously, later on, but this is just as a first run test of what we're doing. So, okay, so in 1D, we've seen improvements, and 2D, we've seen improvements of the joint characteristic function that we have here. But there's no good creating theoretical models. We actually have to test this in real life. So we decided to test this on real world data. So we had to find a dike. Now, one of the best places to find dikes in South Africa is obviously the Bushveld complex. So we went out to the Madikwa Platinum Mine to find some dikes to test this new theory on. So we found a dike that we would like to investigate, and we did initially first some walk mag, so some magnetic data we collect ourselves, thanks to Michael Westgate for assisting me on this. And I know it seems like we're a little bit drunk here at the top, but if anybody knows how the Bushveld bush works, there's like 10 centimeter thorns, so you kind of have to watch where you walk. But we ended up getting quite a good magnetics map to show where the dike is, just so we have an independent data set while we're testing this new empty response function that we've developed. Then we used UBC's MAG3D code in three-dimensional inversion code just to have a better idea of where the dike is, where it's sitting, and the depth of the dike. So this is our, as you could say, our neutral geophysics data set to compare the data to. So now that we know roughly where the dike is that we would like to test our new method on, we then plan two ERT surveys. So the white is showing where the electrodes would be for the resistivity method. And then the blue is showing where the AMT stations are. So yes, we have about 21 AMT stations with a 25-meter station spacing, which is pretty much overkill, but we wanted to make sure we had enough data to do this test. So yeah, this is our general survey, and we really focused on the east-west line here to see if we can see this dike. So just a quick look at the resistivity. We actually managed to see the dike on the west-east resistivity inversion. So this is just the ERT data, not the MT data. And then the north-south inverse model, we actually just clip the dike. So we just clipped some of the edges of the dike, but we mainly focus on the west-east inversion that we see. And that's obviously the data we would like to use for augmenting the magnetotelluric function. So the next step is then to take this and then calculate the augmented magnetotelluric function and see what the difference is in the inverse model. And this is what it is. So the top model, yeah, we have our just our AMT inversion model that we did in WingLink. And I just plotted it in MATLAB just to get the colors. And we can see there's a big north-south fault in the area that is pretty well mapped here. The overburden, you can see, is pretty conductive. So the bushveld has a very conductive overburden, which made it our prime target. But again, we're supposed to see some sort of resistor between 100 and 200 meters. And we do see a bit of a break in the conductive overburden, but it's not really clear to us in this model. But then we take the augmented ERT-MT response function, and then we invert that. And we see that we actually managed to start seeing the resistor dike coming through. And what's interesting, you actually can see two sides of the dike, one being more conductive than the other. And this is most probably due to one side being fracture-hosted water being included there, and the other side being a bit more drier. And we see that we also have a better constraint on the overburden. And again, the fault is still continuous. In this, again, this is just the conductivity is increased because of the simplified current density used in the initial MT calculations. But overall, we managed to map the new dike that we would like to see in our case study. We then compare it to the resistivity, and the resistor feature is in the same location again to the ERT data and the augmented ERT-MT response inversion, just to have a look at that. But I think the nicest image out of all of them was obviously this magnetic inversion with the augmented ERT-MT response inversion. So we have A is where our dike is sitting, and we can see it correlates with the A that we see over here. And then B is where you also see your central fault coming through this area. And it correlates quite nicely with our feature that we see here. Also, another thing to note is you'll see this very dark blue overburden here. It actually fits quite nicely with the MT, the resistivity inversion that we see here. So in general, we improved most probably the actually having a look at just calling some of this resistor feature back that was missing in the original inverse model, as well as the overburden is getting a better mapping as well. So not too bad in recovering the resistive feature. And another side sort of finding that we found is that we did a secondary case study at Moab Khotsong, which is a big gold mine. But the data quality here was horrible because obviously you have an active gold mine and you have a bunch of power lines. And what tends to happen in this case is that your high frequencies are completely destroyed due to the power lines. So if you look here, up to 200 meters, there's just not really enough information that we can use. So we lose quite a lot of our near surface in the AMT inverse model. And that is unfortunate because you would like a more complete resistivity inverse model. But we found then if we just added the augmented ERT-MT response function, because remember, we're just adding that pseudo high frequency data, we actually can refill what has been lost in the high frequencies using the ERT method. So this was a nice side effect that we found from this new method. So, we do get a better sense of resistors below conductors, but we can also then implement a sort of a approach that we can add high frequency data when it's most probably either it's too noisy or it's very difficult to collect the high frequency data. So that was a very interesting side effect from this project. Yes, and then just some considerations is obviously this is all in 2D and we would like 3D modeling in the future to have a look at how we could integrate that for both the transmagnetic and transelectric modes. And that would be a future study. The new method does use a simplified equation for the MT current density, and future work will need a more generalized current density equation, but we were able to show some improvements even on the simplified equation. A lot of these problems can really be solved with a good electrical resistivity survey design beforehand, and doing some fitting of D+ curves and calculating more general empty current density equation. This is all future work that we would love to look at. But this was a good start in seeing how we could at least tackle this problem of conductor features in the near surface, masking some resistors underneath. I would also just quickly like to acknowledge Chimera and the National Research Foundation and Society of Exploration Geophysicists for actually funding a lot of my PhD. I thank them a lot for this. Then UBC, the Geophysical Inversion Facility, for providing the MAG 3D tools to do some of the magnetic inversions. That was a big help for the PhD itself. So I just wanted to acknowledge them. And then just sort of in conclusion, some self-promotion. I am working at SRK Consulting at the moment, and we're doing some really cool work in terms of machine learning, signal processing for different data sets, and even some seismic work. So if you guys would like to contact me on a professional capacity, my email is there, as well as for private email if you have any questions regarding this talk. And yes, thank you. I hope this was insightful and an interesting talk. Thanks, Oleg.
Thank you so much, Wesley. That was really interesting.
Awesome.
We've got one question so far. I'll go through it now, but just a reminder to our audience, if you have any questions, please post them, or you can ask Wesley questions after I go through the questions posted in the chat.
Cool.
So we have a question from Stéphane Duplessis, and he's asking, could this approach be a step towards modeling static galvanic effects in the AMT-MT data?
Yes, it could be, but that's almost a different problem. But there's so much you can do just with this new approach of modeling the electric field using the ERT method combined with the MT. So I do think you can definitely start looking at that, but that'll be a completely separate project. But yeah, that was actually, we actually started with that in mind, but then it sort of branched out into this bigger thing. So yeah, definitely.
Excellent. I'll go to question. I think that the case study you presented was really great from the Bushveld. When you were doing the acquisition, did you acquire both the X, Y, and Z components, or just the X and Y components?
For the MT?
Yeah, for the MT.
Yes, no, but X and Y is required. So we use the Stratagem AMT system. So we use both methods. So both X and Y. So we can get the impedance tensor. So yeah, we use both X and Y components, not the Z component, because we didn't use long period MT for that.
Okay, perfect.
Cool.
Thank you so much. Anyone, any questions? Okay, we have question from Alan. Alan Jones. So your inversion of ERT plus MT was of quasi-MT data from ERT to augment the MT data. That's the question. Or did you modify the inversion code to jointly invert ERT and MT?
Yeah, so this isn't a joint inversion. So we try to stay away from that. So we actually added the quasi-MT data beforehand, and then we put it into the inversion code. So I would love to look later at joint inversions and how this could affect that. But this was just literally just supplementing the existing MT data with the the pseudo MT data from the ERT. But yeah, the joint inversions were really one of the things I wanted to look at a later stage, but we sort of ran out of time with the PhD. But yeah, so it was just added before the inversions were done.
Perfect. And we have a question from Gordon. Do you determine the certainties of your inversion results?
Yes, we do. We use both the RMS standard root mean square. We look at things like the impedance, the phase tensor analyses, the dimensionality analyses, and we also developed a really cool. It's this assessment algorithm that looked at the misfit for cells and data. So we have a full analysis looking at the error just to make sure that it's not errors causing change in the MT and inverse models, but it's actually what we're adding to it. So we have a whole suite of error analysis that we do in MT to have a look at this.
Okay, perfect. Anyone, any further questions? Okay, well, that's pretty much it. Thank you so much. Okay, we have another question from Alan. Just so the problem with resistive imaging is I'm not sure it's a question or a problem or a comment. So Alan's saying the problem with resistive imaging is the reliance on global RMS to describe the distance between the model and the data. Resistive structures are very small effects, so you have to have special attention to the RMS.
Yeah, definitely. Yeah.
And Gordon is asking, how long did the inversion calculation take to compute?
Well, these are quite small models. So from, 10 to 20 minutes in WingLink. The biggest part of MT is processing the data properly. That takes the longest time. Unless you have really big models, then it can take a while. But it doesn't take, in terms of my models, it didn't take that long because it was more on the data quality and processing than it wasn't really focused on the inversion side. So about 10 to 20 minutes in inverse model, but you have to make quite a bit of them just to make sure that your structures stay consistent, to make sure they're real and not imaginary, that they're not temporary structures. So I'd say about 10, 20 minutes, max half an hour if you're running quite a fine mesh. It's all dependent on your meshes as well that you're running.
Yeah, I completely agree with that. My experience as well, 1D and 2D are quite quick. Once you go to 3D, it could take some time depending on the cluster computing resources that you're using to complete the job.
Definitely.
Yeah, thank you so much, Wesley. It's been a great presentation, and Alan saying and everyone saying in the chat that it was a great presentation. Thank you so much for taking us through your work.
Thank you.
And to everyone who could tune in, thank you so much for tuning in. Have a wonderful, safe weekend, and we'll see you next month. Have a great week, everyone.
Awesome. Thanks. Cheers, guys.
Thank you. Bye-bye.